Okay, so let's have a look today at differentiating sine. We'll start with using first principles. So we'll start from the beginning with sine. So if you remember that dy by dx, when we do our differentiation, is the limit as delta x tends towards 0 of delta y over delta x. So if we had a sine graph and we wanted to find the gradient at this point x, remember we say we go a little bit further on, so we choose another point here. If we go delta x on, that point would be x plus delta x. And then the y values here would be sine x. And this y value would be sine x plus delta x. So hopefully you should see then that delta y over delta x would be sine x plus delta x minus sine x all over delta x. And then what I'm going to use is I'm going to use the addition formulae that we looked at to multiply out this bit here. So using the sine a plus b formula, sine x plus delta x will be sine x cos delta x plus cos x sine delta x. So if I sub that back up into this equation, I'm going to get that delta y by delta x equals sine x cos delta y plus cos x sine delta y minus sine x all over delta x. And if I then factorize this top line, I'm going to get delta y by delta x equals, if I take out that middle, cos x sine delta y plus, and then I can factorize the other two by sine x, and that'll give me cos delta. Why have I got delta y? Sorry, they should all be delta x's. These should all be x's, not y's. So I'm going to have, that's delta x, sine delta x, cos delta x minus 1 all over delta x. And what I'm going to do then is I'm going to write this as two different expressions. I'm going to split it up into two parts. So delta y by delta x. So the first part is cos x sine delta x over delta x plus sine x cos delta x minus 1 over delta x. And we said at the start that this dy by dx is the limit of this as that delta x tends towards 0. So this dy by dx has to be the limit as delta x tends towards 0 of delta y over delta x, which is the limit as delta x tends towards 0 of this thing that I've just written above, cos x sine delta x plus sine x, and then it's going to go cos delta x minus 1 over delta x and my big curly brackets. So that's what I'm looking at. And if you want to, this, as delta x goes to 0, that's only going to affect the bits with delta in them. So it's only going to affect these bracket bits here and here. The sine and the cos aren't going to be affected because they're nothing to do with the delta part. So another way of writing that would be to say, well, that's the same as cos x, and then the limit as delta x tends towards 0 of this bracket, sine delta x over delta x, plus sine x times the limit as delta x tends to 0 of cos delta x minus 1 all divided by delta x. And what we now want to know is what happens to these brackets as our delta x gets smaller and smaller and smaller. Now, you may or may not remember from the trig chapter, you had some small angle approximations. So the small angle approximations that we used was that when x is really small, let's say when theta, so when theta is small, then the first one was that sine theta equals theta, and the other one was that cos theta equals 1 minus a half theta squared. So if we use this, we could say, well, if that's the case, then sine delta x would just go to delta x, and cos of delta x would go to 1 minus a half of delta x squared. So if we know that, then sine of delta x over delta x, well, the top line just goes to delta x from above. Delta x over delta x is 1. And then for this one, this cos of delta x minus 1 over delta x. So that would go to, if we put that into our brackets, that's just going to go to a half of delta x. If you sub that in. So if we kind of put those into our equations, then the limit as delta x tends to 0 of sine delta x over delta x is just 1. And the limit as delta x tends to 0 of cos delta x minus 1 divided by delta x, well, that's just the same now as we've said. The limit as delta x tends to 0 of a half of delta x, well, that just goes to 0, because as delta x gets to 0, a half of delta x will also get to 0. And if we put that all back up into this equation, we had originally said up here at this point, we'd originally said that that was what dy by dx equals. So this bit I now know is equal to 1. And this bit I've proved here goes to 0. So it's 1 times cos x plus 0 times sine x. So hopefully then you can see that, well, that will all then cancel down to give you dy by dx equals cos x. And that is your rule. So the rule that we've just proven is that if y equals sine x, then dy by dx equals cos x. And you can do exactly the same thing if you start with cos rather than sine. And that then comes out as saying if y equals cos x, then dy by dx equals minus sine x. And the really important thing about all of this is when we do this, we've used these small angle approximations up here. These small angle approximations are only true when your angle is in radians. So when we do our differentiation or integration, when we come to it, the angle has to be in radians because that's what we've used for this rule. Right, let's have a look at one little example of this then. So if I had something like, let's do y equals sine of 4x, and I wanted to differentiate that. So I know that sine goes to cos, but this is again one of those composite functions or a function of a function. So we're going to need to use the chain rule. Now you may be able to spot this, but if not, if we let u equal 4x, then y is going to be sine u. And dy by dx, we check above, if we start with sine and differentiate, we get cos. That's going to go to cos u. And du by dx just goes to 4. So dy by dx, sorry, that's du there, isn't it? Not dx. So that one's dy by du. So we got dy by dx equals dy by du times du by dx, which is just 4 cos u, and u is just 4x. So it's 4 cos 4x is what my differential will come out with. And we can do the same for any of these trig functions. So if I did it slightly differently and said let y equal cos of 3x squared, then we do exactly the same thing. If you like, we can say, well, let's let u equals 3x squared, du by dx equals 6x, y will be cos u, dy by du, if we differentiate cos we get minus sine of u, and then dy by dx will simply be those two multiplied together. So it'll be minus 6x sine u, which is the same as minus 6x sine 3x squared for my answer. Right, I'm going to just give you a couple of these as a little bit of practice. So can you just copy down and have a go at these few questions? So all I want you to do is find dy by dx for each of these examples. So the first one, y equals sine of 2x, then y equals cos of 5x minus 2, then y equals sine of x squared plus 1, then y equals 10 sine of 0.5x, y equals sine 3x plus cos 6x, and the last one we'll do is y equals cos of x squared minus 3x minus 4. So copy those down, or just pause the video and keep those on screen, have a go at those 6, and we'll look over the answers to those in the lesson on Tuesday.